Hello Cloud Gurus and welcome to this lesson where I'm going to be discussing NoSQL fundamentals. My aim is that this is an introduction only. I'm not going to deep dive into the tech, just provide a basic overview of what a NoSQL database is and how it differs from relational database platforms. Now before we get started, this lesson is going to be split into a number of parts. Each part will discuss an alternative database aggregate model, and we'll talk about aggregate models shortly. But just be aware that each individual mini lesson will be talking about a separate way of representing data. So let's get something out of the way straight away. When we're talking about relational database systems, there may be many different vendors, but they all will be broadly compatible. The differences between relational databases are very small. Vendors attempt to add features which distinguish their products, but due to the standard foundation of SQL, there is a limit to how far products can diverge. So what about NoSQL? Would you assume the same? Well, that would be a wrong assumption. NoSQL isn't a single architecture or view of the world from a data modeling perspective. NoSQL can be defined as a set of products that aren't relational, which cover many different products and architectures. The NoSQL world can be split into two main groupings, those which take an aggregate-orientated view of the world and those which don't. So what do I mean by that? Aggregate-orientated database products deal with blocks of data in groups, and that's their aggregate. This aggregate might be simple, like a key-value pair, or it could be a large, complex JSON document. The premise is that the database treats that aggregate or object as its base level data structure, which is fine if you operate with that same aggregate. If you don't, it can cause you a world of pain. If you and your database don't match aggregates, then you have a problem which has been named impedance mismatch. And it's the same reason why many developers choose not to work in the relational database world, aside from performance concerns. If the data structures they work with in memory aren't the same ones they store, process, and retrieve from their database platform, it makes for inefficient code and a worse product. Over the next few slides, I'm going to talk briefly about some of the differences between SQL and NoSQL, as well as spend some time talking about the main families of NoSQL databases. I'll be explaining the main features and talking about where you might use them within your application. So let's start with the key differences. I spoke in an earlier lesson about relational databases, how a schema is defined for each table, and how this schema is fairly rigid and generally defined in advance before any data is entered. The schema defines the columns and fields for the table, together with the data types and any restrictions. And this means that for a standard employee table, where I'm storing ID, name, and email, I couldn't just add an extra field for one row for the staff member's phone number. In a relational database, we would have to adjust the schema and add the column for the entire table, adding the field for every row. Now with a schemaless NoSQL database, I can just add a phone number field to one row and maybe a pet or a car field to another. Every row can have different fields, and they can be additional fields, optional fields, or completely different fields. There is no enforced schema. This provides significant power and flexibility, but equally your application needs to be fully aware of it. Now there is a small exception to this. The attributes function is the unique ID for each row in the table has to be present in every row. And I say this in inverted commas as some NoSQL databases don't operate on rows, and you'll see this in an upcoming slide. Now consider the ramifications of this. If you can alter data content and structure without disruptive schema updates, this can offer significant availability improvements for your application, and that's one reason why NoSQL databases support 24/7 highly available applications. Much more so than relational database engines, which need sometimes lengthy update schema operations. If the schema operations are modifications, then the data sometimes needs to be fully exported and reloaded to a table. Now, unlike relational database engines, NoSQL systems either don't have relationships between tables and data, or they handle it very differently. This is a key point to understand, as your application will need to be developed to handle this, and your data structure will reflect it. You'll recall earlier when I discussed the process of data normalization. The entire point of that process was to handle the translation of data from its real-world model to a structure which fit into the relational database paradigm. With NoSQL systems, this changes completely, as you will see in the upcoming slides. Be aware of this massive shift in how relationships are handled. Now, normalization as a process, as I said, is generally not required, or at best, less so. The nature of relationships changes, and the DB that you pick is often selected because it fits with your way of modeling data for your application, rather than the other way around. Data is often represented in a much more atomic form, or something with close alignment to the object nature or the aggregate model of your application. You won't have SQL as a language. SQL, as I've described elsewhere in this section, is a language allowing the complex search and manipulation of data within a relational database system. NoSQL isn't relational, and thus we don't have SQL. That's not to say that the database engine doesn't have its own query notation, but this will vary considerably with the technology platform selected. Now, as mentioned above, you will approach database selection based on your needs rather than picking a data model that fits the database. There are many different NoSQL platforms available, and I'll demonstrate these shortly. Now, let's talk about the consistency model. We've got ACID and BASE, and all share the common aspect of being annoying acronyms to remember. But to put you at ease, it's not critical that you know these. Just understand how they impact the choice of a database platform. Let's start with ACID. ACID is a set of properties that govern how a relational database engine processes transactions. It stands for atomicity, consistency, isolation, and durability. And let's look at each of these in turn. So atomicity is a process that describes how a relational database considers each transaction atomic. If a transaction, i.e. a SQL query, has a number of separate components, i.e. for example where 3 attributes are updated, then the transaction will either succeed or fail for all of those 3 transactions. You won't be in a situation where you'll have a partial completion of a transaction, and that's what I mean when I say that a transaction is atomic. Consistency means that on the completion of a transaction, the database is in a structurally sound state. Within relational databases, you can have restrictions on what data an attribute can contain. And consistency means that at the end of a transaction, all restrictions are met, or the transaction does not run as a whole unit. So this links in a little bit with atomicity. The next one is isolated, and that means that transactions do not contend with one another. Let's say, for example, that you have one SQL query that's been applied to a database. It's logical to assume that that one SQL query runs, it makes changes to the database, and then it completes. However, if you've got 100 SQL queries, or 1,000 SQL queries, or even 1,000,000 SQL queries, then on the underside, the database engine is managing those SQL queries. The database is free to apply those operations in any way that it wants, but from your perspective, your SQL query needs to run in a consistent manner that matches the publicized expectations. So if your SQL query does things in a certain way, in a certain series of steps, then it shouldn't matter whether that's the only query running or whether it's one of 1,000,000 queries that run, and that's what isolation means. So lastly, we have durability. And durability states that a successful transaction must permanently change the state of a system, and before ending, the state changes are recorded in a persistent transaction log. Now that means that you're free to use memory caching or any other performance enhancing techniques, but you need to maintain a persistent log of transactions. So as soon as the database engine tells you as a user this transaction is committed, if there is a power failure at that moment, there is a method for replaying that transaction onto persistent storage before it's marked as completed. So the database can do whatever it wants on the underside, in-memory caching, fast caching, whatever it decides, but it needs to be able to cope with a power failure. So the second that it says to you, this transaction is completed and committed, it needs to be guaranteed that that will occur. Now, all of the ACID properties work together to ensure a consistent expected behavior of data transactions to applications. But this does come at a massive cost. It limits performance, especially distributed performance, and it limits the ability to scale horizontally. Now, ACID isn't the only model that's used. It is fairly universal in the relational world, and it worries much more about data safety than performance. Now, BASE is an alternative model, and BASE stands for Basic Availability. And basic availability states that the database should work most of the time, and it's soft state so that stores don't have to be write consistent, nor do replicas have to be 100% consistent all of the time. And it allows eventual consistency, which states that elements of the database will exhibit consistency at some point, but that doesn't need to be 100% of the time. Now, BASE is generally used by aggregate-focused platforms such as key value, document, or column family databases. And finally, we have scalability as a difference. Scalability is actually a product of the consistency model used. Relational databases trade a huge amount of performance and scalability due to them preferencing consistency over performance. And since SQL requires the ability to process multi-table operations, SQL and relational database engines need to ensure that they can handle that, and that also limits the ability to scale. So now, Cloud Growers, I want to spend some time looking at each of the different main types of NoSQL databases. I'm going to keep each different type in its own mini lesson. So this is going to be the end of this lesson. So if you do have any questions, feel free to reach out directly or via the Cloud Grower forums. And if you're ready, please proceed to the next lesson where we'll be talking about key value data stores.